Drake, doing Bachelor of Science in Computer Science, Makerere University. I'm going to take you through a research paper review with the title Advanced Deep Planning Technique for Early Disease Prediction in Cauliflower Plants. It is a scientific report, as you can see, published in 2023. So cauliflowers, as you can see, it is just second most popular call plant, having a lot of health benefits, as you can see. It has different varieties, that is white, orange, and green cauliflower. Then the aim of this research is to understand, enhance understanding regarding the significance of cauliflower disease identification, and then cauliflower disease identification and detection using advanced deep transfer line techniques like ArrestNet and all those. The challenges were a limited number of studies and then lack of comprehensive data set that is properly labeled and of high quality. So the data set used is the VEGNet data set, and 3 classes have been used, that is bacterial spot, black rot, down mildew, and node diseases. And different new transfer line techniques were used, as we're gonna see. Then evaluation metrics used were mean square error, recall, precision, and others. It was found that EfficientNet B1 achieved the highest validation accuracy and lowest rate of 0.16. So the reason, that is the motivation, was just that the traditional cauliflower disease detection methods really relied on subjective human visual inspection, which wasn't really working. Then lack of documentation, relied heavily on expert knowledge, and all those. So what is the solution to this? Due to interaction of AI and machine learning, like different convolutional network algorithms have been used in identifying like different plant diseases, as we're gonna see. So different research has been made by different researchers using different data sets like cauliflower image, VEGNet dataset, the one we've used, and PlantVeg dataset, and using different techniques like DenseNet to predict this, and they have really been accurate in doing that. Hence the need for these researchers to also make a contribution. So it started by introducing or providing this cauliflower image dataset. Then there was data preprocessing, as you're gonna see. Exploited data analysis was made using histogram equalization, and then feature extraction using morphological values, contour features, and others. And then finally, the models were used to learn and predict these diseases, and different evaluation metrics were used. Then after, like a new images provided to this detection model, it can really classify whether it's diseased or not. So first, with data preprocessing, images were resized to 224 by 224 image size. And then this was done by adjusting the height and width. Then the RGB colors were converted to grayscale, that is to increase on the efficiency and then the time complexity. And then 2 morphological operations were used, that is dilation as well as erosion. So this involves like addition or removal of pixels to improve the image quality. Then exploit data analysis, then they used the histogram equalization, which is used to broaden the intensity range. Then it improves the contrast of the images, hence like better training of the models. Then feature extraction was done. Different features were extracted, the area, the shape of the images, then the aspect ratio, extent, equivalent diameter, the contours, the extreme points, and then finding the cropped images. These are all used to training the data sets. Then the models used, they used different models because we have exception model, we have EfficientNet model, Inception ResNet V2, and DenseNet ResNet 152 V2 model. When I go through everything. So for the exception models, just an extension of Inception model. So it introduces like two different decomposition steps, that is depth-wise convolution and point-wise convolution, and applying a one-by-one convolution on different blocks. So the input is divided into 3 segments, as we can see, and on each segment we apply a depth-wise and a point-wise convolution separately. This enhances the ability to capture different features, and then after that we do like batch normalization and ReLU activation to introduce nonlinearity. Then after that, we are doing like global average polling every after a different block. So this is done to reduce the spatial dimension of the feature maps. Then after all the processes, as we can see, we do like the rest. Then we get the dense layers of fully connected neurons with trainable weights for final classification. And then finally, we can do ReLU activation or dropout layers at an average rate of 0.5 to prevent overfitting. And then softmax is done at the end to introduce like different probabilities of these images. Then they also used efficient net model. They introduced efficient net model. This one starts with a baseline convolution that is a depth-wise. Then we do different batch normalization and activations. This can be ReLU activation. So this also utilizes the depth-wise separable convolution, and that is it applies a single filter per input channel. Then we do global averaging. There is rescaling after global average polling. And then it uses the depth-wise convolution and the point-wise convolution of 1 times 1 convolution. So it also incorporates inverted residue blocks. These are not showed here, but here they use the depth-wise convolution V2 as the base convolution on your network, then batch normalization, like different activations. Then dropout is used to reduce overfitting. Then they used inception ResNet 3, which incorporates inception and ResNet architectures. Here, like we incorporate inception, that is consists of a 1x1, 3x3, and 5x3 convolutions, along with max polling operation every after 10. Then we're having an input of 224 by 224 images, and a stem, which is the initial layer responsible for processing the input images and extracting features. And then we're applying the inception ResNet A. That is, we're doing different concatenation, like we concatenate different convolutions together to form a dense net of features. Then like we do auxiliary classifier, which helps to elevate vanishing gradient, which is a major problem with deep transfer learning models. Then we are doing reduction, that is to reduce the spatial dimension of the feature maps before progressing to the next neurons. Then we do average pairing, that is increasing on the spatial dimensions. Then dropout is done to reduce overfitting, and then we do softmax. And we do softmax, then produce the outputs. Then with DenseNet 201, so each layer in DenseNet 201 receives input from previous layers, as we can see. So this allows the network to exploit features learned at different depth, then facilitate the flow of gradient during training. So the transition function is used to downsample the feature map, and then it is used with pre-trained weights. And as we can see, we start with a convolution, then we do a max polling to reduce on the layers. Then we take all the layers to the next layers, and then use a transition layer, as I've explained, when we apply global average polling. Other problems faced by deep transfer learning models are overfitting and generalization, which is a major problem to them. So there's a need for regularization techniques. Then there is data quality and cleaning. Then future selection, because we saw that it's not an easy process. And another computational problem. So some of the strength doesn't require human supervision, automatic feature extraction. It is highly accurate at image recognition and classification, and all others. The weaknesses. So the control feature extraction failed on a few images, which is affecting like the classification and identification of these images. Then bacterial spot rot class contain the images of no disease dataset, which leads to imbalance. Then it requires large amount of data for training, then does not capture all aspects of model performance. So it's only precision, F1 score, didn't see calibration or robustness to class imbalance. Then the complexity of the model would lead to longer training times and increased resource requirements. So the ResNet 152v2 model, this was designed to tackle the issue of vanishing gradient in deep networks, which was major hindrance in developing deep neural networks. So here, like it jumps from one neuron to the next, as we can see. Then there is reshaping and flattening, then different densely connected networks which are activated. And then we can see there is different dropouts to reduce on overfitting. So different evaluation parameters have been used, as we can see. There's accuracy, there is loss, there is RMSE, there's prediction, there's score, and F1. And we've seen that exception is doing far better than most of the others in precision, recall, and F1 score. So another thing, it was the confusion matrix, which shows like the true positives. So exception has like on bacterial spot, it has 18 true positives. Then on black spot, it has 10 true positives, as we can see. So this is just to compare the results. Then another thing, we saw that EfficientNet B1 was performing better than any other model in accuracy, loss, it has the least loss. Then in validation data, it's also working better than any other model. Then another thing, this is the time complexity, so time taken by every model. And we see that EfficientNet B1 took 30 minutes, but EfficientNet B0 took the least number of minutes during training. And ResNet 152v2 took the highest. Then others, we see like different graphical representations of the results. Then the bar graphs showing like different comparisons of the performances. Then like the computational problem is like model efficiency and computational complexity. So they are compute heavy models, and their large size and complexity makes them unstable for deployment on low power devices like the phones and the tablets. That's one. So so there's a need for less complex models. Then the black box nature of these models. All deep neural network models are black box models. That is, like, they can't explain why they do. They just produce the results, and we can't really know like which features they use to bring out like different predictions. So we can't trace or even explain the system